Welcome to our next video in this series on condensed matter theory. In a previous video we have shown that the Hartree approximation can be derived by looking at a state with the lowest energy that can be written as a product of one particle wave functions that are orthonormal. Such a wave function violates the Pauli principle, and we can actually repair that by not looking at a state that is product of one particle wave functions, but looking at a state that we represent as a single Slater determinant and then the lowest energy. So the Hartree Fock approximation is looking at a state with the lowest energy that we can write down as a single Slater determinant. Square root of 1 over n faculty determinant of psi1 r1 up to psi n r1 psi 1 rn up to psi n rn. Or in second quantization, we look at a state with the lowest energy that we can write down as a product of creation operators out of the vacuum. Under the constraint, there are one particle orbitals or one particle wave functions form an orthonormal set. In order to derive the functional form that we get for this wave function and the Hartree Hamiltonian that we get for this wave function, we can again look at the functional derivative, and we take the derivative with respect to the bra of the energy psi h psi minus lambda times the norm of our wave function to make sure that we have our constraints right. If we do this, we get a very similar result as we had in the previous derivation for the Hartree Fock equations. And we need the energy to take its derivative, and the energy is given by a sum over the one particle orbitals times h1 plus a half sum I is not equal to j, and then the direct part or the Hartree part of the Coulomb interaction psi j rj hij 2 psi I ri psi j rj, and then we have the exchange part minus a half sum I is not equal to j psi I ri psi j rj hij 2, and now we have psi j ri psi I rj. If we take a determinant, we have this one times this one minus that one times that one, so when I exchange my coordinates I get a minus sign, and that's exactly what we have here, and we have exchanged it once. So that is the exchange part of the Coulomb interaction. We also know them under the Hartree and the Fock part of your interaction. And we now have to minimize the Hartree Fock energy, which is psi h psi, and naturally under the constraint that our wave function is normalized. So we're going to look at the functional derivative to find the stationary points of the energy of our wave function minus pi I phi I Ri, phi I, Ri, which has to be 0 for some value of lambda. Well, if we take the derivative of this state, then we find here the bra derived with respect to bra is going to be a delta function between I and m. So that is h m1 phi m at coordinate m plus. Now we take the derivative of the second part. That's going to give me two terms, either derivative with psi I or the derivative of psi j. So two delta functions. Sum over j is not equal to m because I took I equal to m. Psi j r j h mj 2 psi j rj times psi m rm plus a half. Sum over I is not equal to m. Psi I ri h I m psi I ri psi m rm. So far we have the same result as we had in the Hartree equations, but now we have the exchange term on top of that. So we have minus a half. Sum over j is not equal to m. I'm taking the derivative with I, so every I is replaced by an m. And the first one is a delta function, so I here have psi j rj h mj 2. Then we are integrating over the coordinate j here, so I want my psi m at coordinate j to be inside the integral, and what we have left is a psi j at coordinate m. And of course we can do this also for the case where we have a delta function between j and I. Psi I ri h I m 2 psi m ri psi I rm. And this has to be equal to em psi m rm, which is basically the constraint minus lambda, and lambda is equal to em, such that we get the eigenvalue equation for our Hamiltonian. But we have to realize now that our Hamiltonian is not a linear operator, so it's not of the form psi m is equal to em psi m, but we have here integrals over the state which we multiplied and then summed over a complete basis set to which we can project to the exchange terms. Nonetheless, also for equations that are nonlinear, we can find the eigenvalues and solve this equation such that we find that this equation holds for a certain discrete set of eigenvalues. And those are the Hartree Fock equations that you have to solve self-consistently to get a solution and a basis set and an effective potential that is now not only given by the direct term of the Coulomb interaction, but also by the exchange term of your Coulomb interaction. So, thank you very much. This is one of the approximations that one can use. And we will, in the next two videos, first look how to write this in second quantization in a bit more general form, and then look at an example where we apply this to the homogeneous electron gas. So thank you very much for your attention, and we'll see each other in the next video. Stay healthy.